Okay, today we're going to start looking more deeply at the world of trigonometry. Trigonometry is a really important area of mathematics to study. It deals with the relationships between the sine and the cosine and the tangent rules of angles, and it's embedded in so much of the physical world in which we live in. The study of trigonometry, the mathematics there underpins our study of waves, for example. So you have waves in subatomic particles in the way that electrons work, but also things like the waves that musical instruments create when you twang a guitar string, and that wave function that is produced is the maths in that is governed by trigonometry and the rules of trigonometry. So it's really important. So much of engineering relies on the rules of trigonometry, from the vibrations of an aircraft wing to how a microwave oven works, to wave mechanics. All these different things all have trigonometry at their heart. So we're going to begin by looking at angles between 0 degrees and 90 degrees. So let us just, whoops daisy, let's do a very simple, quick recap of, we've got a nice little triangle here of theta. R is the hypotenuse, Y is the opposite length, and X is the adjacent. So the sine is opposite, over hypotenuse, theta. The cosine of theta is adjacent over hypotenuse, and the tangent is the opposite over the adjacent. And so we can write that as sine of theta equals y over r, cosine of theta equals x over r, and the tan of theta equals y over x. All nice and simple. So what we're going to do is we're going to play around with some trigonometry and some mathematics as well. So let's think of the cosine of theta if it was root 5 over 3, where 0 degrees is less than or equal to theta, less than or equal to 90. So I want to find the exact value for cosine squared theta. So that would be root 5, that's a 3, root 5 over 3 squared, because cosine squared theta is the same as cosine theta times cosine theta. So we'd have 5 over 9, which is quite simple. Now we want to find sine theta. So let's think about this. Let's think about our triangle. It's a terrible triangle. Drop down here a bit more. Drop up into the line. So we've got our hypotenuse, and here's theta. Now, the cosine of theta was root 5 over 3. And we have the cosine as the adjacent over the hypotenuse. So the adjacent must be root 5. And the hypotenuse must be 3. So we can find, let's make this y, we can use Pythagoras to find the opposite length. So y squared is going to be 3 squared minus root 5 squared, which is 9, minus 5, which is 4. So y must be 4. Therefore, sine theta, which is the opposite over the hypotenuse, must be 4 over, oh not 4, it's a square root, so it's 2, must be, that's 2, must be 2 over 3. And now we want to find the tan of theta. So the tan of theta is the opposite over the adjacent, so it must be 2 over root 5. Nice and simple. Now, I'm going to get a fresh page up and I'll write all these identities again. So we had cosine theta was root 5 over 3, and we used that to find the sine of theta was 2 over 3, and the tan of theta was therefore 2 over root 5. So now we want to find out what would this be. 1 minus tan squared theta all over cosine theta plus sine theta. So let's slot what we know. We've got 1 minus, now tan squared theta will be 2 over root 5 all squared, and then we've got cosine, which is root 5 over 3 plus 2 over 3, and now we're going to simplify. So we'll have 1 minus 4 over 5 on the top, and then we'll get on the bottom, we'll have root 5 plus 2 over 3. So that is going to be 5 minus 4 over 5 over root 5 plus 2 over 3, which is a fifth over root 5 plus 2 over 3. Now, we want, this is not nice, we can't deal with this, so what we're going to do is we're going to multiply the numerator and denominator by 15. Now we're going to multiply the top and bottom by the 15, but why do we do that? Now we see the denominator and the fraction on the numerator and the fraction on the denominator. The denominators of these two fractions are 5 and 3. So by multiplying by 15 we can get rid of them both. So up the top we'll have 15 divided by 5 is going to be 3. And then here 15 divided by 3 is going to be 5, and then we'll have root 5 plus 2. So we're going to have 3, 5 root 5 plus 2. Now, we want to rationalize the denominator, so we multiply by root 5 minus 2 over root 5 minus 2. Now the reason we do that is it removes, oops, brackets back in here, it removes this third from the thing, from the denominator. Now we'll put it up here. So we'll have 3 root 5 minus 2 plus 2, sorry. No, minus 2. Looking at the wrong bit. And then here we have 5 in the bracket, root 5 plus 2, root 5 minus 2. So we have equals to 3, root 5 minus 2 over 5. Root 5 times root 5 is 5, and then we're going to have we'll have root 5 times minus 2 root 5 plus 2 root 5, and they'll cancel out. Then you'll have minus 4. So if we work all that out, we end up getting a breakup in that bracket. So we have 3 root 5 minus 6 over 5. And that's in the simplest form that we can get that into. So this is quite a complicated one. And so it's these wee tricks here where you want to kind of simplify the fractions, and you're thinking, what can we multiply through to do that? And then down here, when we want to rationalise the denominator. So this trick here of multiplying by the root 5 minus 2 over root 5 minus 2 gets rid of that bit at the bottom. And these are tricks that will often prop up in A-level maths problems. So just with the sheer practicing of doing these types of problems, you get used to these tricks and how to apply them. So let's look at something else. So it's really useful to know the exact values of certain angles. So we're going to think about the exact angles, set values of the sine, cosine and tangent, that is, of certain angles. And namely, these angles are 30 degrees, 45 degrees and 60 degrees. And to remember to be able to jump between the degrees and radians, so that would be pi over 6, sorry, pi over 4 and pi over 3. So let's think about what these look like. That is not what I wanted to draw. I want it to look more like this. So we're going to think about an angle. We're going to think about 45 degrees first. So if a right angled triangle, that's going to be 90, and for this to be 45, this must be 45. So we must have an equilateral triangle, and for making it easy, let's make these two sides 1, and we can use Pythagoras to find the hypotenuse. So that would be the square root of 1 squared plus 1 squared equals the square root of 2. So this is the square root of 2. So we can think of I'm just going to write that up there just now and leave it. Now we can think of another triangle. This time we have 60 degrees. Now 60, half of 60 is 30. So that's like thinking about another equilateral triangle here. And if we had that would then be 60 there, and we've come down here for 90. We would then find, if we had this is 1, and this would be 2, this would be root 3. because we've got the perpendicular bisector to our equilateral triangle, and it splits the base here. So that would be 1, that would be 1. So the equilateral triangle is base 2. And we then get these two right angle triangles that are the same. And that's how we then get our root 3 by, again, using Pythagoras. So let's now create a table. So we'd have sine theta, cosine theta, and tan theta. And we're going to have our angles. We're going to have theta equals to 30 degrees, and 30 degrees is the same as pi over 6. We have theta equal to 45 degrees, and that's equal to pi over 4, and theta is equal to 60 degrees, and that's pi over 3. Now this table that we're drawing is actually something that is really useful to memorise. So sine for 30, so we're thinking about this angle, so it's going to be 1 over 2, so it's a half. Cosine of 30 is going to be adjacent over hypotenuse, so it's root 3 over 2, and the tangent is going to be opposite, so it's 1 over adjacent, which is root 3. Now the 45, which is this one up here, 45 degrees, so the sine of 45 degrees is going to be opposite over hypotenuse, which is 1 over root 2. And for an angle of 45 degrees, the cosine is actually the same. And the tangent is going to be just 1. So that's quite an interesting result. Now the sine of 60. So for the 60 degrees we get root 3 over 2. We have, for the cosine, we have 1 over 2, and for the tangent we have root 3. And if you were to compare 60 to 30, you can see the sine and cosine are flipped, and the tangent is the denominator is now on top, it's just root 3. And so this actually gives us an indication of some deeper relationships that are in play between sine, cosine, and tangent. So we're going to do some examples of why this is important. Also, I'm going to put this down here because this is a top tip. 1 over root 2 is the same as root 2 over 2. And we did that, but if you were to multiply, but you've just basically rationalised the denominator. You've multiplied the numerator and denominator by root 2, and that gives you that. Likewise, 1 over root 3 is the same as root 3 over 3, because we're always going to be, for these examples, we always rationalise the denominator. So we've got sine of 30, cosine of 45. We want to find that value. So we go to our table. Sine of 30 is a half. Cosine of 45 is 1 over root 2. So it's going to be 1 over root 2. But if we look here, that is the same as root 2 over 2, because we rationalise the denominator. Oh, that's 2 root 2, sorry. So that's going to be 4. So this bit here becomes root 2 over 2, and then multiply that 2 by 4. Gives 4. Next one is going to be sine squared pi over 3, which is the same as sine pi over 3 times sine pi over 3. So pi over 3 is 60 degrees, so that is root 3 over 2 times root 3 over 2, which equals 3 over 4. And you can't do anything with that. Now we're going to do something a bit more tricky. We're going to do 2 cosine pi over 4 sine pi over 6 all over cosine squared pi over 3 plus sine squared pi over 3. Now that's the squared, not 2 times pi. So let's get what we need out of the table. So we've got 2 times cosine pi over 4, which is going to be 2 times 1 over root 2 times sine pi over 6 times a half all over cosine pi over 3, so it's a half squared plus sine squared pi over 3 root 3 over 2 squared. So the 2's here are going to cancel. So we've got 1 over root 2 all over, so that's going to be, we're going to have 4's on the bottom, so that's a 4, and we'll have 1 plus root 3 here. Oh no, it's squared, so that's going to be 3. Sorry. So that's 3. It's squared. So that is 1 over root 2. So that's going to be 1 plus 3 is 4 over 4. So that's just 1. So that just gives us 1 over root 2. Now we're going to times, rationalise the denominator, which we were talking about earlier, and that's going to be root 2 over 2. So I hope that helps.